Okay, so I am going to be recording chapter 15, part two. And it's been a while since I recorded the first part. I lost the second part video, so I'm here re-recording it, and hopefully this goes well. So to quickly recap, we introduced this chapter already, the equilibrium chapter. I went through some examples, and so I'm going to continue from here. Depending on how the question is stated, of course, you will write what is given and then what is requested, right? So for 15.5, we are finding the equilibrium constant from experimental concentration measurements. Okay. Once again, please excuse all the format issues. Right here, the equilibrium sign is not showing. In the place we have that F symbol. It's supposed to be an equilibrium sign. So we're given an equilibrium equation, okay? And we're given amounts of the reactants. And in this case, of the reactants, and then we don't have products in the beginning, and then we're given the amount of one of the reactants at equilibrium. Sorry, I'm a little bit slow to start today, but I'll get there, okay? So for us to be able to make sense of this, let me go ahead and show this part right here so I can add a page. Okay. So what I'm going to do here is read what is given to us. Let me write the formula down. So we have CO, this is a gas, plus 2H2 gas. And then I'm going to write my equilibrium arrows here. So I actually got a chance to cover this on Wednesday on campus. So that's just 2 days ago. So hopefully I still remember. Okay, so what they're doing here is showing us how to set up what is called the ICE table. So I haven't talked about the ICE table. The ICE table is a means to an end. It is a table that is designed to help us ultimately figure out equilibrium concentrations of reactants and products. And it also helps us, it facilitates our being able to figure out the equilibrium constant. Since this problem wants you to find the value of equilibrium constant, you want to use the ICE table. When I was in school, the table didn't really have a name. I shouldn't say it didn't have a name. If it had a name, the teachers weren't sharing, right? So when I said teaching and I read this book, I was like, wait, this has a cool name. No pun intended, right? Because it's ICE. Anyway, I know. So the ICE table here, right? I doesn't stand for ICE. Look at me, I'm so caught up in the story. It stands for initial. So I stands for initial, referring to you will place all the initial amounts right here in the first row of your table. C stands for change. And the change here actually goes with stoichiometry. So we're going to go back to 1411 and look at the stoichiometry that tells you how much of each reactant reacts relatively, right? Relative amounts, and then how much of each product is supposed to be formed. Okay, then finally, since this chapter is all about equilibrium, the E here will stand for equilibrium. If we were using the ICE table, oh, by the way, you can use the ICE table in one-way reactions. And in the one-way reactions, the E will stand for the end, right? Or I guess end. But in this context here, E stands for equilibrium. So we're bringing in the use of the ICE table. Okay, let me go ahead and build my ICE table, or I guess draw it in. The table looks like this. And once again, it's a means to an end. Kind of like long division is this multi-step process that helps us divide numbers, right? This is a multi-step process that helps us to find the equilibrium amount. So once again, we have the initial amount here, the change based on stoichiometry, and then we're going to have the equilibrium amounts down here. Once we have the equilibrium amounts, right, which we're going to solve, then we can find the K of equilibrium, the equilibrium constant. So I haven't mentioned this yet, but since this K is essentially an equilibrium constant, for us to solve for it, we can only use equilibrium numbers. So the numbers we write here for the product raised to the power of the coefficient can only be equilibrium numbers. We cannot put initial numbers or change numbers. We can only put equilibrium numbers to get the equilibrium constant. Does that make sense? Okay, so we have here reactant raised to the power of the coefficient. Of course, if you have multiple products, you will put the other products here. If you have many reactants, you put the other reactants here. You get the gist, right? So anyway, let me leave this here for right now. Let's go ahead and get our equilibrium amounts. Okay, back to the question. They tell us a reaction mixture at 780 degrees Celsius initial, that means the numbers right after that are initial numbers, contains, for CO, the concentration is 0.500. So here we have 0.500 molar. The numbers we put in the ICE table is usually molar amounts, okay? And then for H2, initially we have 1.00 molar. And then period. It says nothing about the product. So if we're dealing with the initial, this is assuming that the reaction has yet to take place, right? We haven't mixed the reactants yet. We just have CO in a container and we have H2 in a container. They have yet to be mixed to form the product. So we have 0 molar amounts of product. Okay. And then the reaction happens, and then fast forward, bam, we are at equilibrium. So when we are at equilibrium, they didn't really discuss this, right? This is implied. It had to happen because the only way to get from the initial to equilibrium is a reaction has to happen. So now we're at equilibrium. We're told at equilibrium, the CO concentration is 0.15, implying that at equilibrium, some reactant has reacted, right? When we do a roll call, we discover we have 0.15 molar of CO left. How do we stop this? Oh, I didn't know how to stop that. Anyway, we have 0.15 molar of the CO, carbon monoxide, left. Okay, you know, for us to find the value of the equilibrium constant, we have to have all these numbers here filled in, then we can plug them into this equation right here. So let's go ahead and fill in the numbers. So in 1411, we talked about balancing the equation, right? And we balanced the equation with the multipliers or the coefficients. And so this equation is balanced, and the number implied here is 1. The number shown here is 2. The number implied here is 1. So we're saying for this reaction to take place, we need 1 amount of CO, right? So for every 1 amount of CO that reacts, we need 2 amounts of H2. The amounts happen to be molar amounts, right? So 1 amount of CO, 2 amounts of H2 to form 1 amount of CH3OH. Now, the amount doesn't always have to be 1. It's just telling you the relative amount. Whatever amount CO, I should say, delegates to reacting, H2 matches that amount by doing twice. So whatever CO does, H2 will match it by doing twice. So it won't really match the same amount, but it has to do it twice. So for what I mean by that is if CO chooses to give half, right, which is 0.5, H2 has to do 1 because the relationship has to be 1 to 2. If CO chooses to give 2, H2 has to give 4 because once again, they have to maintain that 1 to 2 relationship. It's almost like anything you can do, I will outdo it. I can do better, right? I'm not going to start singing, but yeah, that's the stoichiometry here. If whatever CO does, H2 does twice. Okay, that's what the balance equation is saying. So, understanding that we already have the equilibrium amount of CO, right? I need to mention something. To get the equilibrium amount, you take the initial amount and then you add the change. Okay, for that reason, we're told here we have what? 0.15 amount of molar of carbon monoxide. And then we're given the initial amount. The initial amount was what? 0.500. I think it's like this. And then 000. Or is this 2 zeros? I don't know what I'm thinking. I don't know. Anyway, you all get what I'm saying, right? Let me do this over. So we got 0.15 left over, and we started with 0.500. So what is the change? When you subtract this both sides over here, and then minus 0.1500, I will get it eventually. We end up with the change being 0.35 negative, right? 0.35 negative. So here we put negative 0.35 molar. So if you take 0.5 minus 0.35, you get 1.5. Remember, the negative here indicates the reactant is used up during the course of the reaction, right? It's not being made, it's being consumed. The reactant is being sacrificed by being consumed so that we can make products. Over here, the same thing is happening. Reactant is used up. Okay, since the amount that reacts for H2 has to be double the amount of CO that reacts, I'll take this number here. It's still negative because it's reacting. And I'll double it and put 0.70 molar, right? Because that's double, correct? On campus, I usually have my students helping with the math, but I'm here by myself. It's a Friday and I'm tired. But let's see. This will go well. Yes, I verified that. It's 0.7, sorry. Now, in the change, we also have the products. Whatever amount reacts here, the same amount is formed here. So over here, since we are making a product will be positive, and it has this amount here, it has to match the CO amount, so it'll be 0.35 M. So made, therefore positive. So from here on, I'm not going to write these explainers or explanations in the table because I have defined that here. Just make sure you go over this part. Don't skip over it, okay? Reactants are decreasing, so they'll be negative. Products are being made or they're produced, therefore they'll be positive. To get E or equilibrium amounts, just add the top number to the bottom number. So here we're going to get what? 0.300, right? And then here we have 0.35. Okay, so let's go down here. Just make sure, the table shows what we have. You see, they show you initial amounts of the other reactants. Here, they're showing you how it works out. They're doubling the H2 amount. And then we have that, and then we have this, right? So we have 0.15, 0.30, 0.35. Okay, I want to make sure before I move on, because I do feel a little bit fatigued. But let's continue. Now, we saw how we get to this part right here, right? So let me go ahead and clean this. I hate this new system they have where if you get out of bounds, it resets the eraser tool, so you're not erasing anymore. Now you're writing. So I have to stay within bounds there. Okay, great. Finally erased. Now I can solve for my K equilibrium. To write my K equilibrium or to solve for it, first you have to write your equilibrium expression based on your balanced equation. My product is what? CH3OH. That's my product. Raised to the power of 1. The 1 is implied. And then over the reactant CO raised to the power of 1. 1 is implied over the reactant H2 raised to the power of 2. The 2 is right here. Okay? So for this part here, you have to place the equilibrium amounts. So for this part here, the numerator, this number will be this. I didn't put the units consistently here. Oh my goodness, this is what fatigue does to me. I'm a little bit more careless. So I have this M here, this M here. So I have 0.35 molar, right? Divided by this number here is going to be what? 0.15 molar. And then here I have 0.300 molar, but I have to square this number. So go ahead and plug this in. I'm not really showing a calculator here. Let me see if I can actually pull up a calculator to kind of fill up the space here, because I have this whole space that is showing nothing. Give me just a moment, okay? Because I recognize sometimes when I'm typing in numbers and then giving you guys the answers, some of you are just watching what I'm doing. You want to practice entering the information yourself so you're getting the correct answer. Sorry. Okay, let me move this out of the way. Move that out of the way here. And then I need to get the calculator, right? Calculator. That way I can describe how I'm entering numbers, right? Let's see, calculator. Okay, we got that over here. Let me make this skinny. Y'all give me just a moment. Make this skinny. Maybe zoom this out a little bit so y'all can see the screen I'm using to do the math. Okay. Okay, let me zoom this out a little bit. Oh, great, right there. Okay, so for the numerator, open parentheses, right? 0.35, close parentheses, divide by, since this part is going to be the bottom, I want the calculator to recognize those numbers as the bottom, right? Denominator. So I'm going to use the parentheses to do that. open parentheses again, open the parentheses, and then 0.15, right? That's this number right here. Close parentheses. Open parentheses again, that means you're multiplying by this number right here, 0.300. And then here I'm going to square. Do we have a square function? I guess this is square. Oh yeah, square. Close parentheses, close parentheses. So it should recognize that whole number on the right, the 0.15 times 0.300 squared, as the denominator. Let's see how it plays out. 25.9? Let's see. Does it work out here? 25.9? 26? Yes. Okay. So let me go back there and write in my answer. So it does work out as K equilibrium is 26. Okay. Once again, you guys saw how I entered. Make sure you practice using your calculator, because if you're working since you're working on multiple choice exams, if you don't know how to enter your number in the calculator, you will do all this work and then select the wrong answer or end up with the wrong answer, right? You don't want that to happen. Though it seems tedious, it's an important skill for you to learn. So spend the time. Okay, so I started my lecture here yesterday with reaction quotient. So we have a reaction quotient, right? What exactly is a reaction quotient, you ask? So let me go ahead and detour a little bit and I'll come back to this. So I'm going to add the page right here and I'll come back to the slides. Okay. Remember how I just mentioned that K equilibrium, this equation can really, I'm going to put P for product because I'm tired of writing the whole word, can only handle equilibrium numbers, right? And then you have the coefficient here, coefficient. These numbers have to be the numbers at the bottom of the ICE table, right? The bottom row that says equilibrium. They can only be equilibrium. You cannot put any other numbers in here. It can be equilibrium, I should say here, only. Same thing with this one here, equilibrium only. But what if the question gives you initial numbers and then it doesn't really want equilibrium numbers and it wants you to do something else with initial numbers? What do? You can't use this formula here. So you're going to use the same formula. Let me show you. The same formula. You will use the P here with the coefficient. I know. I just said you can't. Now I'm telling you can't. So which is it? It's both. Let me show you how you can. Okay. This is the kind of things that chemists pull. If you change this right here and call this reaction quotient. Oh, how do I move this over? Okay, hold on. The same formula. I know you're seeing the same formula and call it the reaction quotient. Quotient. Now you can place initial or equilibrium numbers. Now you can place initial or equilibrium numbers. The idea is there is more flexibility when you're figuring out the reaction quotient than when you're figuring out the equilibrium. Equilibrium constant can only accept equilibrium numbers. Reaction quotient, why is that a frame? Reaction quotient can accept initial numbers or equilibrium numbers. That means if you have a question where you're not exactly sure if the numbers are initial or equilibrium, and you're not sure, you want to find the reaction quotient. Now, the formula is the same, but the meaning of the word or the value of it is different. Okay. So if that's the case, why do we want to find the reaction quotient? Because remember I told you guys earlier, they can give you initial numbers and have you do something different. But what is that something different? Okay. Here's the thing. If you're giving a reaction, for example, I'm going to give you guys this number right here, H2O2 to give us 2H2O. If you're given this reaction, right, and this is balanced, and they tell you the amounts here, let's say the amounts are 0.100 molar, 0.100 molar. I'm just making these up. And then here we have 0.500 molar. Let's say you encounter these reactants and products in a reaction. Okay, now all three are present. Just because all three are present doesn't mean we are at equilibrium. Even though to be at equilibrium, you have to have all reactants and all products present. Okay, so we check and we realize this reactant is present, right? Hydrogen is present, oxygen is present, water is present, and then we want to say it's at equilibrium. You can't just jump and say it's at equilibrium. Reactions that have equilibrium arrows or that have a potential to get to equilibrium, they tend to have an equilibrium constant tied to them. Okay, so there is a table somewhere that has the published amount of equilibrium constants for those reactions. So instead of speculating and saying, well, I checked my reactions and I saw that all the reactions were present, all the products were present, therefore it had to be at equilibrium, you will go to that table, find the equilibrium number, right? And then you will use the math you have right here. You will use the expression to find the value here. And if the number here matches the one you found in the table, then you can say, yes, this reaction is at equilibrium. Okay. So for us to make those kind of judgments, and I didn't really explain it in class like this yesterday. Hopefully, if they can watch the video, they'll get an alternate view of what I said, right? There is a table, an equilibrium constant table that tells you what the equilibrium constant is for the reaction. So once you find that number, you can then figure out Q, the reaction quotient. And of course, the reaction quotient is based on the reaction and the initial concentrations. So when you find that, so I'm just going to give you guys some numbers here. Let's say the table showed that this reaction here had an equilibrium value of, I'll just say here, 0.750. I'm just making up this number, y'all. Just making the number up. Okay. That means when we find the reaction quotient, our reaction quotient has to work out 2.750. And if it does, and Q is equal to the K, which K indicates we have arrived at equilibrium, then we can say if Q equal K, we are at equilibrium. If Q is not equal to K, then we are not at equilibrium. So I'm not going to do the math here. I just want to show you guys how this plays out. So there are situations where Q might be bigger than K. That means you got to equilibrium, then you overshot, you kept going, right? Or Q can be less than K. That means we haven't even reached equilibrium. Of course, then we can have Q at K. So I feel like I'm getting ahead of myself, right? Okay, so the purpose of the reaction quotient will tell us how the reaction will change, either by going to the right or further left to get to equilibrium. So let me go ahead and read the text. If a reaction mixture contains both reactants and products, if a reaction mixture containing both reactants and products is not at equilibrium, right? Implying just because reactants and products are there doesn't mean it's at equilibrium. How can we determine in which direction it will proceed to get to equilibrium? Remember, the goal is always getting to equilibrium. The answer is to compare the current concentration to the equilibrium constant. Equilibrium constant, once again, is a number that tells you you have arrived at equilibrium. If we can somehow get a number called the reaction quotient, right, that has the same formula like the equilibrium constant and compare that number to this number, then we can make an objective judgment as to whether our reaction is at equilibrium or not. So I already showed you guys that, okay? Essentially, if you look at this right here, for this generic reaction, for concentrations, our reaction quotient formula is just the same as equilibrium expression, right? Or equilibrium constant expression. Same thing with the pressure, the same as equilibrium constant expression when we're dealing with pressure. So let's go ahead and see. Now, I told you guys this before, right? That the quotient can be above equilibrium value, it can be below equilibrium value, or it can be at equilibrium value, okay? So let's go ahead and unpack this. Now, keep coming back here to show you what this means. I told you guys before, I am not good at memorizing, okay? If memorizing is your gift, then go ahead and work your gifts. Do what you do naturally and you do easily to learn the content. Me, memorizing is not my gift, so I have to work harder to understand. The thing with working harder to understand, it's a lot of work up front, but it's kind of like I feel like it's kind of like a retirement account, the 403B. I know how did I get the y'all. Not 403B, sorry. It's like the Roth IRA where you pay your taxes now, you do the hard work, you pay the cost now, and then you kind of coast to the end. So with me, when it comes to understanding, I have to do a lot of work to understand. I have to really do I have to front load the work and do a lot of work to understand, connect the pieces. But once I do that work and I arrive at understanding, then it's easier for me to coast. Okay. But then recall is just so much harder for me. And then when I recall, I unrecall. Like when I learn, I unlearn. Anyway, back to this. Y'all know I can just go on and on. Okay. We will calculate Q. Once we calculate Q, we'll compare it to K. So for us to understand what this symbol means and how it plays out right here, I am going to add a page here, a blank page, and then we're going to try to understand. If it feels like it's too much for you, just go over it and then move on. So a scenario where Q is greater than K. Remember, I told you guys, since my goal is to understand, when I was reading this before, there were things that were not being communicated. There were patterns I started to notice. One of the things I noticed was the reaction was always trying to get to equilibrium. So we're going to add a goal here that is implied by not clearly stated. Goal is to reach equilibrium. Okay, it's somewhat implied. It is indicated or kind of referred to, but not necessarily clearly behind the moves. Our goal is to reach equilibrium. The way we get to it here is by getting to whatever the K is at equilibrium, right? Whatever that K number is at equilibrium. Once we get to that number, we can say we are at equilibrium. That would be like our objective test. Okay. So for us to work on this part here, I would say I have to assign a value to K. Let's say our value of K is 100, okay? And then I have Q here being 1,000, okay? Our standard is 100. We want our equilibrium constant to be 100. Well, sorry, our equilibrium constant is already 100. We want the calculation to yield 100. Since our reaction quotient is bigger than 100, it's at 1,000, our goal here is to somehow decrease to reach this number right here, correct? Because this 1,000 is bigger than 100. If we can decrease it, we can reach 100, okay? Well, how do we decrease it, you ask? I shall tell you. Let's go back to that relationship between the equilibrium constant expression and the reaction quotient. We said the reaction quotient Q is equal to product raised to the power of the coefficient over reactant raised to the power of the coefficient, right? Like that. And essentially that is the same thing as the equilibrium constant expression. That is your reaction quotient. I also mentioned before that the numerator parts influence each other directly, right? So if Q is large, then P is large also, right? Because they have that numerator relationship, they affect each other directly. And so whatever Q is relatively, these are just comparing. If we judge Q to be large, that means there is a lot of product, okay? The product amount is large. Relatively, that means the reactant amount is small. These are all relative terms. We don't really have numbers tied to them, right? We judge the Q to be large based on comparing the Q to the K. So we know in the equilibrium reaction, your reactant is on the left, you have your equilibrium arrow, product on the right. So if we want to decrease Q, right? We want Q to go down, to decrease. We want to decrease this. The way to do that is directly by decreasing the product. If you decrease the product, you, in the same process, increase the reactant, okay? Because you decrease the product by reacting it out, and therefore you make less product, or you have less product by reacting some of it and then making more reactants. So we decrease the product by shifting reaction to the left. In the process, product amount decreases. So product amount decreases, right? And decreases means it gets smaller. Now, you know the relationship here. As long as P is smaller, it will cause Q to be smaller. And reactant amount increases. And this is the result we want. We want the reactant to increase and the product will to decrease. And when we are able to do that, we are able to actually drop the Q. Remember, Q will go from 1,000 to 100. Once it reaches 100, we reach equilibrium. And then, of course, the amount of reactants and products will remain constant, right? While the rate of forward and the reverse are equal. Anyway, so over here, we'll say shifts left. Okay, so let's go down here and see what they say. Oh, so was it done? Or yeah, it was done. How did I go far up? Okay, if Q is bigger than K, the reaction will proceed faster towards the reactant side. The products will decrease, the reactants will increase. So you all have seen it, have seen why. Okay, for this part here, for the next part, let me see if I can work it out here and I can just zoom out because it was a lot of scrolling. This time here, we're looking at, once again, we're comparing Q versus K. And we're saying that this time Q is less than K. So Q is less than K. So K is still 100, okay? And let's make Q this time equal to 10. So Q we know is equal to product raised to the power of the coefficient over reactant raised to the power of the coefficient. Based on this number being 10, our Q is less than what we want it to be. We want to be at equilibrium. So the Q has to increase, okay? It has to get higher. It has to increase and become, how do I show that? Q has to become bigger. So we have Q here. It has to go from being 10 to being 100, right? If we're judging Q as being small, which we are, smaller than what we desire, that means our product amount is also small than what we desire. And the small product is what's causing the Q to be small, right? And that means the reactant amount is large. For us to make the Q get bigger, we have to manipulate the reaction. Once again, the reaction has reactant on the left side, products on the right side. So we have to make this reaction move in such a way that we use up some of the reactant making product, we shift to the right. When we shift to the right, we then decrease the reactant, increase the product, right? Increasing the product will cause Q to become bigger because they have that direct relationship, okay? So here the reaction will shift to the right. So shifts to the right to get to equilibrium. Hopefully you see that backstory. So when we scroll over here, it says once again, when Q is less than K, the reaction will proceed faster towards the right side or product side. It's not saying the reverse reaction isn't taking place. Just the one that we want to increase becomes more dominant because it's trying to help the reaction get to equilibrium, okay? And in the process, we have more products, less reactants, and then we get to equilibrium. Okay, so what if we have scenario 3 or bullet point 3 where Q is equal to K? Since I told you guys before the goal was to be at K, the equilibrium, in this case, K is 100 and then Q is 100. So what do? Nothing. We have arrived at our destination. We are at goal, so do nothing. Do nothing. Correct? Because we have arrived. Remember, our goal was to get to 100 because K is 100. If you're at 100, why would you do anything? You've arrived. Moving on. Okay, since my goal is to explain what is written here, it says, if the reaction mixture contains just the reactants, Q is equal to 0 and the reaction has to proceed forward. Okay, to explain that statement, this goes back to what I was telling you guys earlier, okay? Our goal is to reach equilibrium. At equilibrium, if we have two reactants, the first one and the second one, right, to give us products, first one and the second one, then we know that if we're at equilibrium, all reactants and all products have to be present, correct? When you check them out, they all have to be present, and they have to be present in constant amounts. The reaction has to be at a place where the amounts present are constant. So if you're starting a reaction with only reactants, right? And there's no products yet, but the goal is to get to equilibrium. You have to make products first and then get all the chemicals to be constant before you can actually get to equilibrium. So the reaction has one direction to go. It will go to the right first, right? Correct. Make products, product one and product two. And then at some point, so the way it starts, even though we're drawing it the way we're drawing it, remember the way it starts is it starts one way first. It starts with a forward reaction most of the time, right? And then you make enough products, and then the products begin to react to form the reverse reaction. So this is what happens first, and then the reverse happens, and then you have the same rate for forward and reverse, and then this is pretty much equilibrium. But you have to form products first. Okay, so back to the value of Q. Since Q is equal to product over reactant, raised to the power coefficient. Now, yeah, I'm shortening this. I'm trying to conserve my energy. In the world of mass, since we started this problem saying there was zero product, we can say here the amount of product, zero. Amount of reactant, we don't know, but it's some number. Any zero divided by any number equal zero. So mathematically, when we have a reaction mixture containing just reactants, Q ends up being zero. And the reaction has to proceed in the forward direction to make products. Okay, what if the reaction mixture contains just products? So remember I told you have to have all reactants, you have to have all products. So in this backstory here that we're looking at, we have only product one, product two, right? Since you have to have reactants and products to have equilibrium, the reaction will proceed in the reverse direction, right? Forming the reactants first. And then at some point when you have enough reactants, they will react to reform the product. And then we have equilibrium when all of these amounts remains constant. So how do we get the infinity? In this case here, having the same relationship, Q is P over R. This time we have only a product raised to the power C, and we have zero for the reactant because we had zero reactant. In mass, any number divided by zero is infinity. Feel free to plug that in your calculator. Let me try it over here and see. I'm curious. Okay. How do I clear this up? Clear. Oh, AC. Okay. So let's take 6 divided by 0. What does it give us? Infinity. You see that? So any number divided by 0 is infinity. Wait, am I sharing this? Oh, yeah, I am sharing. Okay, sorry. I wanted to make sure because I normally it looks red around here when you're sharing. Yeah, we're sharing here. It looks red. Okay. Oh, yeah, sorry. It says you're screen sharing. My bad. No, listen to the reason why I'm saying that. I have recorded all videos, like the whole hour and a half video, and then I realized I forgot to press share. Because from my end, it looks the same, right? Kind of. And I'm like, no, a whole hour and a half of work. Okay, we get a chance to practice comparing Q and K. In comparing Q and K, you see right here, where are we at? Let me add a page. We're going to solve for Q and then see how that plays out. So I am going to be, let's see, what happened to the square one? I remember the square one that we used to have. Let me copy this right here. Oh, there it is. Huh. I don't like updates. Updates means it's something new I have to learn. I mean, it's great and all, but it's something new I have to learn. Okay, so this is our equation right here. So I'm going to write the amounts. We have the pressure of I2, this number here, as point 0.144 atm. And then PCl2, we have 0.102. And over here, we have 0.355 atm. Let me see if I can squeeze this here. 0.102 atm. Yeah, that will work. Because I want to draw the ice table so you can see. So for this part here, it says the reaction mixture contains this amount here, right? Is the reaction at equilibrium? So I was going to draw the ice table. I won't because I don't even know where to place the numbers. I mean, you can place them in the beginning, but yeah. So for this one here, we're just going to figure out if the reaction is at equilibrium. Our target is to get to 81.8, 81.9, right? So we'll find Q. Based on the balanced equation, Q is equal to this product right here, the expression ICl raised to the power 2, right? And since we have pressures here, I made this mistake yesterday where I put concentration. You have to write the pressure of ICl raised to the power 2 divided by these pressures here. Pressure of I2 times pressure of let me go back, Cl sub 2, right? And this is balance. Okay, so I'm going to plug in the numbers here for our Q. Pressure of ICl will be 0.355. You're going to square that. And then ATM, of course, squared. Oh, my goodness. Brain. No, this is just what fatigue is doing. It's been a long week, so my brain is just like, I need a vacation. Okay. PI2 is what? Was it 144 or 114? It was 114. I know I said 114 and 144, y'all. Sorry, but you see what fatigue does to me, right? Okay. So 114 atm times, and then PCl2. The Cl2 here is what? 0.102. Right? I have to double check because I know I'm operating tired. So when I'm tired, I make a lot more mistakes. Okay, there. So we have to square this number. So I'm writing it less so I can see. Let me work it out over here. I'm going to try to work it out in one go. Let me clear that. Okay. So in one go, I have to use parentheses here. Open parentheses, 0.355 square. This goes here. You put square, close parentheses, right? That's my numerator. This part here is done. I can't put units here. The units will cancel out. Okay, now my denominator divide by, I have to open parentheses to represent the bottom. 0.114, right? And then, oh, you know what? I need another parentheses here. Will it allow me to do that? To click here? Will it? Or I haven't put the other one. Let me see what happens if I put times here. Okay, that will work. You can put a times here if you have parentheses under the bottom number. Let's see. 0.102. Close parentheses. So it understands this is these together. The product of this is the bottom number. Let's see how that plays out. Okay, we get 10.8. Okay. So let's go over here and make sure we got the same number they got. Oh, look, 10.8. Great. Okay. We know 10.8 and the target was, oh no, we're low. This is low. We need the 10.8 to go up to 81.9. So we need this to go up because right now we're judging it as low, right? For it to go up, that means this side here has to go up and this side here has to go down. So if we need the Q to get up, we need the product side to increase. So products must increase. For us to do that, we need the reaction to shift to the right. Reaction must shift right to make more product. When the product amount increases, even though the process will have less reactant, that's okay. We don't mind sacrificing the reactant to make more product. When the product amount increases, it will actually increase Q. Eventually 10.8 will become 81.9. Does that make sense? So it says right here, the reaction is not an equilibrium. Oh, I didn't say that. It was implied. And we'll proceed to the right to make more product, because when we have more product, then Q becomes bigger, right? And eventually this number becomes that number. And then we arrive at equilibrium. Okay. For this part here, we're trying to find equilibrium concentrations when the given equilibrium constant initial concentrations or pressures. So we're trying to find equilibrium concentration when given equilibrium constant and initial concentration or pressure using ice. I won't read those directions. I'll just show you how to apply the directions. So for this part here, I tend to skip over this problem. Yay. Okay. Let me tell you why I'm skipping over it. I forgot to delete it. I'm skipping over it because you cannot start something new with a remix, right? People have to kind of see the original first. So I feel like this question is a little bit too advanced for the beginning, so I'm not going to do that part. I forgot to remove it. Okay. Delete. Delete. Let me delete that too. Where's the delete button? Delete. And it has quadratic equation. Come on. Will we do the next chapter? Yes. I'm going to save all that great fun stuff for next chapter. And we're going to be, when I say we are going to be rested, I mean, I am going to be rested. Yeah. We do quadratic equations in the next chapter. You get to enjoy that then. But for right now, I want to ease you guys into this process first, and then we can do some fun other things. Okay. So actually on campus, I did a different problem in its place, right? So I want to get to do that here too. I want to add a page and just give you guys a different random problem. So say, for example, we're going back to the whole making of water. We have H2 gas plus O2 gas, and this gives us 2H2O gas, right? And we have 2 here. Say we're told that given, oh, sorry, I have to write the problem above because I need to draw the ice table here. Given 0.100 molar of H2, 0.100 molar of O2, and 0.500 molar of H2O at equilibrium. Find K equilibrium. Okay, so in this problem, the amount you're given, you're told, is at equilibrium. It's at E, not at initial, not in the beginning. So in my ice table that I have here, I can skip over my initial. Okay, I don't have to write anything here because they already gave us the amount that we normally use the ice table to find the equilibrium amounts, but they already gave that to us. So I can write here, the amount here is 0.100 molar, the amount here is 0.100 molar, the amount here is 0.500 molar. So the next step I have to do is just go with my expression. I don't have to fill in the rest of this. Does that make sense? Okay. So over here, we have our equilibrium expression. I can use K, not Q, because these numbers are equilibrium numbers. That will be what? H2 amount raised to the power 2 over H2 amount raised to the power 2 O2 amount raised to the power 1. That's implied, right? So you don't have to write that part there. Okay, we already have the H2O at equilibrium. That was what? 0.500 raised to the power 2. And then for H2, we have 0.100 raised to the power 2 for O2, 0.100, like that. So once again, I'm going to enter these at once, together, because my teachers were doing that in school, and I was like, man, that's so much. It's a little bit more complicated to learn how to enter it, but it's less mental wear and tear on your brain, right? So you make less mistakes in future problems. Let's go ahead and set this up. Okay, since I have to square this, I may want to put parentheses around this one. So I'm going to use 2 parentheses, open, open again. I want to do it like this so that this doesn't get lost in there. Okay, so just a precaution. 0.500 squared. Oh, I forgot I could do it inside. It's okay. It's okay. I forgot I could do it inside. Okay. It's fine. I'll have the extra parentheses. It won't hurt anything. The bottom one, I want to have two parentheses for sure. So the top one, I didn't need the second parentheses, right? Okay, bottom one, I need, this is point, oh, let me go back. 0.1, that will work. 0, that has to be squared. Oops, how do I delete it? Delete. Oh, great. 0.100, click, yes, squared, close parentheses. So I want you to square that number. And then, of course, multiply this by, open parentheses, 0.100, close parentheses. Okay, there's a bunch of parentheses here. I just want to make sure that when I'm writing these in here, the numbers look right. Okay, so this looks like this. Y'all can see it. That looks like that, ish. And that looks like that. Okay, let's see how that works out. And of course, 250. Oh, I forgot I made up this work. So yeah, it looks right-ish. Okay. So when you're reading questions, pay attention. Are you given equilibrium numbers or initial numbers? Okay. Let's go ahead and work on this problem now. In this problem, we're told you are given the equilibrium constant, not the numbers, and initial partial pressures. So for us to do this, we have to use the I table and add the numbers to I row, not E row. Does that make sense? It has to go to the I row. Okay, let's see. How do I get this here? Copy. I'm going to paste that. Okay, so this is our equation right here. Oops. Right here. So we're going to have initial change equilibrium. Okay. A reaction mixture 25 degrees Celsius initially contains. So we have 0.100 atm for I, 0.100 atm for P, and then 0.100 atm for ICl. Oh, sorry, this is not P, this is Cl2, right? I'm looking at this right here. These are the pressures we have initially, right? So I think I wrote it in the right place. Now they say they want us to find equilibrium partial pressure, the ones at E, given the value of K. So since they didn't give us any number ahead of time for equilibrium, we have to find all the numbers for all the reactions and all the products. For now, we'll use X as the placeholder for the change, okay? Once again, we said here, because we have a 1-to-1 reaction ratio, that means whatever amount of I2 reacts, Cl matches it, Cl2 matches it. Okay. If one reacts here, one reacts here. If three reacts here, three reacts here, because the mole ratio matches. Right? So since we don't know the amount that reacts here, we're going to say, what if X reacts? So what if X of I2 reacts? Then X of Cl reacts also, because remember, whatever number is here is matched here. Okay. One way you can look at it is the coefficient you write in your molecule or your formula will match the coefficient here. So if it was 3 here, this would be minus 3x. Does that make sense? And if it was, say, 5 here, to balance it out, it would be minus 5x. The coefficient in the balanced equation has to match the coefficient of x, because x kind of represents that reaction. Okay, let me see if I can erase this. Okay, finally, back here. So minus x, okay? We have 1 to 1 to 2. So here we'll have plus 2x because this is our product. Let's go ahead and add this up. I don't have a lot of room, so I'm going to write as 1.1 minus x. I don't want to put the zeros here because it will crowd the numbers. Then here, same thing, 0.1 minus x. I didn't put the zeros here because it will just get very crowded. And here we'll have 0.1 plus 2x, right? Remember how we find E? We find E by adding I to C. Okay. So once we have this, then we're going to find the equilibrium expression. Kp is equal to the pressure of ICl squared divided by the pressure of I plus the pressure of Cl. No, plus, sorry. I was focused on something and then I forgot to say. This is supposed to be times. Yeah. Excuse all the mistakes I'm making. This is what happens when I'm very tired, okay? But I'm hanging in there. I'm pushing through. So yeah. So we got Kp equal PICl. We got that. We got this. Okay. Let's see. Let's plug in our numbers. We haven't covered the 5% rule. I don't think it applies here just yet. I wish I could erase these. Let me see. Can I erase these numbers without some of that space there? Snap. That's okay. I'll write them like this. Or erase the lines, I guess. Man, I have to re-record this later. I am misspeaking. Yeah, it's okay. Okay, let's see if we can work this out here. So we got this. What is Kp over here? Kp is given to us as 81.9. Plug in the numbers here. We have 0.10 plus 2x squared over, we have 0.1 minus x times 0.1 minus x. Okay? So in the world of chemistry, we try to simplify our math. So we're going to consolidate the bottom number, and it's going to be 0.1 plus 2x for the top number. I haven't done anything to that one. The denominator here will be consolidated. Since it's the same number in the parentheses, we'll square it. 0.1 minus x. This would be squared. This would be 81.9, right? And then consolidate this part even further. So first we consolidate this bottom part. Now we're doing the top part. It becomes 0.1 plus 2x. Actually, let me see if I can remove this here. Divided by 0.1 minus x. And then the whole thing is now squared. This is 81.9. Okay. So you want to take a square root of both sides to get rid of this, right? And so we end up with 81.9 square root of that number. I get 9.05. So 9.05, right? $81.9, the square root of that. Yeah, 9.05. Okay, this becomes equal to 0.1 plus 2x divided by 0.1 minus x. And then divide by 1 here to do a cross multiply. Multiply this into that and this to that. I'll do this part here first. Okay. We get 0.1 plus 2x is equal to 9.05 times 0.1 minus x. Then we're going to go ahead and distribute this. Multiply this into that. Multiply this into that. Let me get some water here. Okay. So this works out to 0.905, right? When you multiply this by this. And then the other one ends up being 9.05x. And then 0.1 plus 2x. So we want to bring all the... how do I change the highlight? Oh, that's the number. We want to bring the variables together, right? So what I'm going to do here is add 9.05x to both sides. 9.05x. That zeroes this out. So now we have 0.1 plus 11.05x equal 0.905. So to get rid of this minus 0.1 minus 0.1, this zeroes out. We end up with 11.05x equal, when you subtract this, what do we get? 0.805, right? Let me verify this because I don't trust myself doing head math when I'm tired. 0.1. Yep, that was correct. Divide by 11.05. Divide by 11.05. But I'm trying to do this to work my brain, right? Because it's like a mental workout. Divide by 11.05. So we get 0.072885. We'll make it 9. Okay, so how about that? We got that for x. Once you have that, you go back all the way here. Since you got what x is, you can then replace these numbers that are written as x with actual real numbers. Whoops, 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 whoops. 0.0729. 0.0729. And here you're doubling. So let me go ahead and double the number first times 2. I get, oh, here. Let me delete this. Oh, delete that. Ah, come on. Okay. 2 times 0. This is plus 0.0729, right? So here I get 0.145. I guess 1 4 is 6 ATM. And then let me divide that by 2 to get the original number. And then let me see. So I'll take, oh, I forgot. I forgot and I did my math on the calculator. Y'all, it's fine. Okay. So I forgot I had a calculator there. So I'm going to have 1.1 minus 0.0729. So I get 0.027. 0.0276. Okay, that makes more sense. Yeah, the issue I had is because I completely erased the number, so I forgot to add the 0.1. Okay,